Okay, so let's start out with a fairly simple pressure vessel problem. So we got this pipe, inner diameter of 12 inches, wall thickness of 0.25 inches, valves closed, and the pressure is increased to 300 psi. So if we are going to be assuming this is a thin-walled pressure vessel, we need a certain kind of thickness to, a certain radius to thickness ratio. So our radius there is 6 inches. Our thickness is 0.25 inches. So we got 24. So that's exceeding what we should expect. So that's reasonable. So based upon that, we can just go ahead and say that our hoop stress, that is the pressure times the radius divided by the thickness, share 300 psi. And I just calculated that ratio already, so times 24. 300 psi. So that'll give us a hoop stress of 7.2 ksi. There's a terrible looking equal sign. There we go. Then our longitudinal stress, P times R over 2T, which is just going to be half what we just calculated. So I'm going to go ahead and just hit divide by 2 on my calculator. And we get 3.6 ksi. So yeah, not exactly the most complicated calculations, which is exactly why we make assumptions like this is the thin-walled pressure vessel in the first place. It really does simplify things, doesn't it? So that's relatively simple. Let's go to something maybe a bit more complex. So here we got this gas pipe supported by concrete piers laying on the ground. And we're saying here that essentially they're saying that the concrete supports there don't move at all. So when we have a temperature rise of 70.5 degrees Fahrenheit from the temperature it was installed, what do we have happening? So essentially what we're going to have here is we're going to have the pressure that is going to be so we're going to have two combined effects. The pressure is going to cause a bit of stretching of the pipe. First off, the temperature rise is going to cause thermal expansion, and then we're going to get a force that's going to contract, and a force kind of generated by these supports is going to be pushing back on that expansion. So essentially what I'm saying here is our boundary conditions result in a strain. Let's strain longitudinal equal to 0. So let us figure out kind of how much it would need to push back and what the resulting longitudinal and hoop stresses would be as a result. This shouldn't affect our hoop stress, so we'll just go ahead and calculate that first off. So our hoop going to be equal to P R over T. Inner diameter of 10 inches, a thickness of 0.25 inches. So inner radius of 10 inches. Sorry, I skipped ahead. Inner diameter of 20 inches, which is an inner radius of 10 inches. So 10 inches divided by 0.25 is our R over T ratio. That's 40. And then multiply that by our internal pressure of 600. That gives us a hoop stress, 24 KSI. So we've got the let's see here. So we've got we want to figure out what our strain is. Our total strain is 0. And that is going to be equal to the longitudinal stress divided by the longitudinal stress that would otherwise just be induced by the pipe, divided by E, plus the thermal expansion. So that'll be alpha delta T minus the kind of reactive forces. We can think of it as a force, or we can just think of it as what sort of stress level would be. Oh, we'll do both. We'll figure out what sort of stress needs to be induced by the what sort of stress would need to be induced, just like sort of essentially what sort of compressive stress is there just as a result of the need to restrict that expansion, and then we'll figure out what sort of forces that we're going to get kind of in between the pipes as well. So that'll be I'm going to call it sigma comp for compressive. And again, that's divided by E. So if we want to go have a look at so we know the material is A36 steel. So again, we can kind of we can go back to our textbook here, have a look at A36. So we know our modulus of elasticity equal to 29 KSI. Oh wait, no, 29 times 10 to the 3 KSI. Or you know what, I always like to do 29 times 10 to the 6 PSI. So I find it easier to just be working kit in pounds. And we know it's so that's its modulus elasticity. And we also need to know what its thermal expansion coefficient is. So its coefficient of thermal expansion is, what do we do? 6.60 per degree Fahrenheit. Sorry, 6.60 times 10 to the negative 6 per degree Fahrenheit. Okay, so again, this is 0. So 0 is going to be equal to our longitudinal stress, which is half our hoop stress, So I'm going to put 12 KSI there. 12. $12,000 PSI divided by our E, 29 times 10 to the 6 PSI plus the thermal strain that would otherwise be induced just as a result of the heating. 6.60 times 10 to the negative 6 per degree Fahrenheit times, what was it, 60 degrees Fahrenheit that it raises. So now degrees F cancel out and we're left with some sort of strain minus this all over E. Now, you know what, I'm gonna, okay, so solving for that, okay, so we got 12,000 divided by 29 million. That gives us 4.138 times 10 to the negative 4. And then we got 6.6 e negative 6 times 60 plus 3.96 times 10 to the negative 4. So add those two things together. That'll be 8.098 times 10 to the negative 4. And we can multiply out by our E, or by our Young's modulus, in order to just get the kind of compressive stresses that would be induced. $29 million PSI, which ends up being 23.4948 KSI. So essentially, the actual stress state in the longitudinal is just going to be the combination of that compressive plus the longitudinal stress that's just inherent in that pressure setup there. So what we're ending up with here is we're ending up with an actual stress state, R theta Z, that is going to be, so R is still 0, our theta, so thetas are hoop, so theta is still 24 KSI. Actually, I'll put the KSI on the outside. And $11.48 negative here. So essentially, when we get the combination of the okay, so you'll when we get into failure theory later on, you learn that this is worse than if we just had the original of 24. The original stress state, if it was just the just induced by the pressure vessel, it'd be 24 and 12 here. So it's pulling, 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 and pulling versus the stress state that we got now, which is pulling, pulling, pushing, pushing. That ends up being worse from a perspective of, is this object going to fail or not? But you'll examine kind of how to calculate that and how to predict the failure later on in the course. But yeah, there we go.